This presentation is all about cellular energetics. We'll first look at the laws of thermodynamics, types of reactions, and then we'll end with a discussion of ATP. If you're taking an outline of our notes, here are the topics we'll focus on. First, we have to review a few definitions, then we'll get to the laws of thermodynamics, types of reactions, and we'll end with ATP. First, let's look at a few definitions. Matter is probably a word that you've heard many times before. Matter is just simply anything that has mass and takes up space. So air is matter, water is matter, the cells in your body are matter, and so on and so on. Let's move on to see the different types of energy. Energy is the ability to move matter or cause changes in matter. So to move things around or to rearrange the atoms that make up a molecule. Another way of saying this is energy is the ability to do work. There are two types of energy. That's potential energy and kinetic energy. Potential energy is the energy an object has due to its position or the arrangement of its atoms. If we look at this rock on the cliff, it has a high potential energy because it's high on the cliff. If it were to drop down, its position is lower and then it would have less potential energy. Same with this spring right here. If the spring is compressed, the spring would have a high potential energy, and then if you let it go, this potential energy would go down. Bonds between atoms store energy. So the more bonds you have in a particular molecule, the more energy that molecule can store. When bonds in a molecule are broken, the potential energy of that molecule decreases. But when you release that energy, you can use that energy to do work within a cell. Kinetic energy is the energy of an object in motion. So now let's compare potential energy and kinetic energy. This guy at the top of the hill, if he's not moving, if he's just sitting there, he has a high potential energy. When he's going up, he's moving, so he has some kinetic energy there, and then he has some kinetic energy here when he rolls down the hill. The total amount of energy is going to stay the same, just you can go from kinetic energy to potential energy or from potential energy to kinetic energy. Don't forget, potential energy is energy due to an object's position or the arrangement of its molecules and atoms, and kinetic energy is the energy of motion. Now let's look at the laws of thermodynamics. We'll look at the first and second law, and then we'll look at Gibbs free energy. The first law of thermodynamics states that the total amount of energy cannot be created or destroyed, but it can be transformed from one form to another. So if we look at a roller coaster, if these guys are moving, if they're sitting at the top of the hill, like before they even start rolling down, they would have a high potential energy, but they're not moving very fast, so they would have a low kinetic energy. At the bottom of the hill, they would be moving very fast, so they would have a high kinetic energy, but based on their position, they're not very high, so their potential energy would be low. But the sum of potential energy and kinetic energy is going to stay the same. Here's another example of the first law of thermodynamics. During photosynthesis, you're going to be forming bonds between atoms. So you will be storing energy in those bonds. But the energy had to come from somewhere. You can't just create energy from nothing. In photosynthesis, that energy will come from the sun. And then through photosynthesis, you will use that energy from the sun and store it in the bonds of glucose. So you're not creating energy, you're just transferring or changing the form of that energy. The second law of thermodynamics states that every transfer of energy increases the entropy of the universe. So every time you change the form of energy, the amount of disorder will increase. Here's some examples of increasing entropy. Let's say that you spray some air freshener in the corner of a room. At first, the air freshener is highly concentrated in the corner of the room, but due to diffusion, those particles will spread out. All right. To begin with, the particles are close together and they're highly ordered, but over time, those gas particles will spread out. They'll become more disordered, so the entropy will go up. So here's some examples of highly ordered and disordered energy. Heat is disordered energy. Heat is not as usable as energy stored in bonds, so heat is not useful energy. Bonds are ordered energy. So if this brown bear over here has energy stored in the bonds of his fat and he runs around, his body might break down that fat, break those bonds, and use that energy that's released to move around. That would be kinetic energy. But some of the energy is also lost as heat. So you went from a highly organized form of energy, those bonds that are holding the molecules of the lipids and his fat together, you break those bonds and release energy. And some of the energy becomes very unusable. That would be our heat. It's not useful. It's disordered energy. Now we got to look at Gibbs free energy. This is a formula that you're going to see on your formula sheet. You do not have to memorize it, but it is pretty easy to remember. You do need to know what the components mean. Gibbs free energy, or just free energy for short, is the portion of a system's energy that can perform work. The formula is delta G equals delta H minus T times delta S. So we need to define these variables. G is free energy, or Gibbs free energy. You can use either term, Gibbs free energy, fine. The delta means change. So whenever you see this little triangle here, that just means change. So delta G is the change in the free energy. Delta H, H is going to mean enthalpy. Enthalpy is basically the energy remaining in the system, the energy that's still there and is still available to do work. The delta, again, just means change. So delta H is change in enthalpy. Don't confuse the words enthalpy and entropy. You need to memorize the difference between the two. T is obvious, that's temperature, and we're going to use temperature in Kelvin. Don't forget, Kelvin is the degrees in Celsius plus 273. And then finally, delta S, S is going to be our variable for entropy. So delta S is the change in entropy, or the change in disorder. So you might say, why on earth do we care about measuring delta G? This is not a math class. Well, we care about delta G because it helps us to determine if a reaction will happen spontaneously or not. Reactions with a negative delta G occur spontaneously, or can occur spontaneously. But if a reaction has a positive delta G, that reaction does not occur spontaneously. That doesn't mean it doesn't occur, it just means it requires an input of energy to occur. So delta G, so reactions with a negative change in Gibbs free energy can happen spontaneously, but if they have a positive change in free energy, they cannot occur spontaneously. Don't forget that this G means free energy. So if I say change in free energy, this would just be a shorthand way of saying change in free energy. All right, so now let's look at a couple types of reactions. We have exergonic reactions and endergonic reactions. The name of the word sounds like it's a definition. Whenever you see exergonic, I want you to think, energy exits. So energy is going to exit from an exergonic reaction. This results in a net release of energy. Therefore, it has a negative delta G because you're losing energy, you're releasing it. And that energy can then in turn be used to do work. Your exergonic reactions, since they have a negative delta G, can occur spontaneously. Whenever you see endergonic reaction, I want you to think energy enters. So energy enters an endergonic reaction. So endergonic reactions result in a net gain of energy. Therefore, that has a positive delta G. Remember, delta G just means free energy. So it has a positive delta G, and they cannot occur spontaneously. You don't just all of a sudden add energy to, or the energy cannot all of a sudden increase in a system. It has to come from somewhere. So exergonic reactions, energy exits. You're releasing energy to do work or whatever. Endergonic reactions, energy enters. All right, a couple more reactions. We have catabolic reactions. Catabolic reactions are metabolic reactions. Just think of your metabolism. So it's a metabolic reaction that releases energy by breaking down complex molecules into simpler molecules. Another way of saying this, like the noun form, would be catabolism. Catabolism is a reaction where you take more complicated molecules, so molecules that have lots of bonds in them, and you break some of those bonds. You don't have to break all of them, but you're breaking it down into a simpler form. So that's a catabolic reaction. Whenever you say the word catabolic reaction, think catastrophe. In a catastrophe, things fall apart. Like the World Trade Center was a catastrophe. You started with the two Twin Towers. They fell down, they fell apart. They went from the highly ordered World Trade Center towers to, all of that debris on the ground. So catabolic reactions, things are falling apart, and that results in a release of energy, because energy is stored in the bonds of the molecules, and that energy, when those bonds are broken, has to go somewhere. It's released, and that can be used to do work. So are catabolic reactions endergonic or exergonic? Well, if you look at the definition, it says catabolic reactions are metabolic reactions that release energy. So they're losing energy. energy, so the energy might have been stored in the bonds and then it's released, so you have a negative delta G. Therefore, they are exergonic reactions. An example of a catabolic reaction that occurs in your cells is cellular respiration. You break down the highly ordered organic molecules you eat in your food to release energy, and that happens inside of your mitochondria. So cellular respiration is an example of a catabolic reaction, which is exergonic. You release energy that your cells can then use to do work. The opposite is an anabolic reaction. An anabolic reaction is a metabolic reaction that synthesizes or makes a complex or complicated molecule from simpler compounds. So it's the exact opposite. If you want to form bonds between atoms, energy has to come from somewhere. Energy is stored in those bonds. So you have an input of energy, you use that to arrange your simple molecules into something more complicated, and that requires an input of energy. So the question is, are anabolic reactions endergonic or exergonic? Well, if they require an input of energy, they are endergonic reactions. So a way you can remember anabolic, think anabolic, you add things together. So anabolic starts with an A, add starts with an A. So you're adding molecules together, simpler molecules together to make something more complicated. That's anabolic. Catabolic, think catastrophe, you're falling apart. An example of an anabolic reaction is photosynthesis. Photosynthesis takes simpler molecules like water and carbon dioxide and then combines those atoms, rearranges them, forms bonds to form a more complicated organic molecule known as glucose. And so you get a more complicated organic molecule, and you would need an input of energy to form those bonds. That energy comes from the sun. Now let's look at ATP. ATP stands for adenosine triphosphate. ATP is the energy currency of a cell. Cells cannot just take in light and all of a sudden do things. They have to use the energy from the sun, if they can do photosynthesis, and then use that to make ATP, and then you can do things with that ATP. It's the energy currency of a cell. Energy is released when the phosphate bonds of ATP, and we'll see what this looks like in a second, are hydrolyzed. This word hydrolyzed means you add water to it to break them apart. Think hydrolysis. Hydrolysis is a noun. Hydrolyzed would be the verb. So if it's hydrolyzed, you add water to break the bonds apart. So the energy that's released when you break the phosphates off of ATP can be used to drive reactions in a cell that need an input of energy. Those would be endergonic reactions. So let's see what this looks like. Here's ATP. You have adenosine, that would be right here, triphosphate for the 3 phosphates here. If you break a phosphate off, so you see that one phosphate has been broken off, we call that inorganic phosphate. You've now released energy. The energy that was stored in this bond is released, and then you can use this energy to in turn perform endergonic reactions within a cell. So ATP is kind of like a battery. You can charge it up. You start with ADP. ADP stands for adenosine diphosphate, di meaning 2. And if you add an inorganic phosphate to that, then you now have ATP. And then if you lose that phosphate, that releases energy, and you can use that energy to do work. So this is the hydrolysis of ATP. If you add water to ATP, you can hydrolyze ATP, which means start to break it off or break it apart. So if you break one of those phosphates off, it's lost as what's known as organic phosphate, and you're left with ADP, and then you have energy, and you can use that energy to do work within a cell. So again, the reactions in a cell that require an input of energy are endergonic reactions. So ATP synthesis, or the formation of ATP, requires energy. So if you want to add a phosphate to ADP and make ATP, that requires energy, but if you break that phosphate off, that releases energy. That's known as ATP hydrolysis. So ATP hydrolysis, or the breaking apart of ATP by adding water, releases energy. So finally, let's talk about how ATP drives cellular work. So if a cell wants to move something from a low concentration to a high concentration, that would be active transport, and it requires an input of energy. You would need a carrier protein that pumps the molecules against the concentration gradient. So the way ATP comes into play is you can't just say, oh, it adds energy. Well, actually a terminal phosphate, or the last phosphate from ATP, will break off. Now you have ADP, and that phosphate will go bind to the carrier protein. That's known as, it will phosphorylate, or you add a phosphate to the carrier protein, and that energizes the carrier protein for a certain amount of time. And then that when you add the phosphate to the carrier protein, that carrier protein can then pump things against the concentration gradient. Another example of this would be your motor proteins within a cell. Motor proteins are just proteins that are used to move things within a cell. Remember from our cell unit that vesicles carry things within a cell, and you have these fibers within a cell that are kind of like train tracks, so that's your cytoskeleton, and motor proteins actually attach to both of these guys and can move the vesicles along, kind of like a train track, and ATP helps in that process. Basically, a phosphate will break off of ATP and it will bind to the motor protein, and that energizes the motor protein. So that's a lot, I know. I hope that's helpful. If you have any questions, feel free to ask.